Welcome to this explainer. Look, today we're diving straight into the incredibly high stakes of violating an environmental operating permit, and exactly how we keep emissions in check inside a power plant. As an operator or a power engineer, you know perfectly well that keeping the lights on is really only half the battle. The other half? Making absolutely sure that what comes out of your stack doesn't trigger massive fines or, worse, serious environmental damage. So here is our roadmap for today. We're going to cover the flue gas challenge, scrubbing sulfur dioxide, controlling thermal NOx, selective catalytic reduction, particulate and chemical conditioning, and finally, the operator's loop. We'll be starting right at the heart of the action inside the furnace, and we'll follow the journey of the gas all the way up the stack, breaking down the exact chemistry and mechanics used to clean it up.
Section 1. The flue gas challenge. To kick things off, we've got to look at the root of the problem. Burning specific fuels generates highly acidic gases, right? And these gases, particularly oxides of sulfur and nitrogen, are the primary culprits behind acid rain, ozone depletion, and greenhouse gas effects. From the plant's perspective, they are a direct threat to your operating permits. Every single facility operates under strict legal limits, and crossing them means severe penalties.
So, understanding flue gas desulfurization, or FGD systems, is literally your primary tool for staying within those legal limits. You can't just treat these systems as optional accessories. They are massive, highly complex chemical processing units integrated directly into your mechanical workflow.
Section 2. Scrubbing sulfur dioxide. Let's look at how we specifically tackle this pollutant, usually referred to as SO2. Now, SO2 is born directly from the sulfur and mercaptans present in specific fuels, especially coal and heavy oils. Basically, if it's in the fuel, it's absolutely going to try to get out of the stack. As an operator, your playbook for reducing SO2 really boils down to 3 distinct methods. Which one you pull from the playbook depends heavily on where your plant is located and what kind of cost-effective fuels you can actually get your hands on. You can just switch to a cleaner fuel, you can try to scrub the fuel before it even reaches the burner, or, and this is what you see in many large-scale operations, you rely on FGD mechanical equipment to literally capture the SOx right out of the flue gas.
To picture how that FGD equipment works, just imagine crushed limestone or a lime slurry being sprayed directly into the gas stream. The lime chemically reacts with the sulfur dioxide. Through this kinetic reaction, calcium sulfite reacts with oxygen to effectively trap the sulfur, creating calcium sulfate. You're taking a toxic acidic gas and turning it into a solid byproduct that can just be safely removed. It's a brilliant piece of chemistry.
Section 3. Controlling thermal NOx. Moving on from sulfur, we have to talk about nitrogen oxides, or NOx. This requires a totally different mindset. Because while sulfur comes directly from the fuel, NOx is largely a product of the combustion environment itself inside the furnace.
Thermal NOx is the real enemy here. It's produced when regular atmospheric nitrogen gets exposed to the insanely high temperatures of your furnace, and that whole process gets accelerated by the rapid mixing of fuel and air. The huge takeaway here? NOx production is an exponential function of temperature, meaning if we can figure out a way to lower the peak heat of the flame and slow down that mixing process, we can practically choke off its formation right at the source. Think about the core dilemma you face when tuning a boiler. Are you going to starve the flame of air or stage the fuel? With air staging, you limit the primary air to drop that flame temperature, and then inject the rest of the air later on. With fuel staging, it's the opposite. You create slightly oxygen-deficient zones and then add secondary fuel downstream to finish off the combustion. Both of these strategies are trying to do the exact same thing: stretch out the combustion process and eliminate those extreme concentrated temperature peaks where NOx just thrives.
Now, 80%. Just think about the sheer impact of induced flue gas recirculation. By simply routing some flue gas back to the boiler furnace right near the burners, you can achieve up to an astonishing 80% reduction in NOx. And honestly, the best part is that you don't even need dedicated new fans or complicated new mixing devices to do it. It's just a wildly efficient use of your existing thermodynamics.
Beyond the actual structural design of the plant, you also have some temporary operator tricks up your sleeve. When your load permits, taking your highest top burners out of service while leaving their air registers wide open forces the lower burners into a fuel-rich state. That one simple manual move can cut NOx by up to 20%. Other methods include utilizing fluidized bed combustion, since it naturally operates at lower temps, or even injecting water or steam directly into the combustion zone to literally cool the fire down.
Section 4.
selective catalytic reduction, or SCR. But what happens when tweaking the furnace simply isn't enough to meet those strict environmental permits? Well, that is when we turn to post-combustion cleanup, using a system called selective catalytic reduction. You'll see this widely used on both boiler exhaust and gas turbines.
300 to 400 degrees Celsius. This is not just a random range. This is your absolute Goldilocks temperature window for the SCR system to even function. The flue gas has to be cooled to this exact window before it hits the parallel plates or ceramic honeycombs that are coated with vanadium, platinum, or titanium catalysts. If that gas is too hot, your catalyst gets damaged, but if it's too cold, the chemical reaction just doesn't trigger, and you end up venting toxic gas straight out the stack.
So let's look at the actual chemistry happening inside that perfect temperature window. You inject a solution of ammonia, usually right around a 5% concentration, into the flue gas just upstream of the catalyst grid. As the gas and ammonia hit the catalyst together, they react. Mathematically speaking, 4 molecules of NO and 4 of ammonia combine with oxygen to transform into harmless nitrogen gas and water vapor. It's honestly a beautiful piece of chemical engineering.
Section 5, Particulate and Chemical Conditioning. Okay, let's see how this all builds into the final cleanup stage. This is incredibly relevant for aging plants that are suddenly being forced to meet the super strict particulate limits of modern permits. Because let's be real, sometimes retrofitting a massive new baghouse or precipitator just isn't physically or economically possible. So, what's the workaround? Chemical conditioning. By adding specific chemicals directly into the flue gas, we can drastically boost the collection efficiency of the equipment we already have. For instance, operators might actually burn molten sulfur on purpose to create SO2, run it through a converter to make SO3, and then shoot that into the ductwork. The SO3 alters the electrical properties of the fly ash, making it way easier for the electrostatic precipitator to grab. But of course, there's a catch. Excess SO3 can create this highly visible blue or brown haze right at the stack. And as any operator can tell you, a glowing colored plume is the absolute fastest way to get a very angry phone call from your environmental regulator. If that happens, you've got to immediately deploy an atomized liquid spray to knock that specific haze right out of the plume.
And speaking of precipitators, optimizing their electrical fields is this constant, ongoing balancing act. It's a simple, step-by-step, closed-loop logic that your automated controller uses. To get maximum collection efficiency, the system constantly raises the voltage between the electrode wire and the collection plate. It pushes the voltage right to the very edge of a cliff until it detects a microscopic spark. The split second it feels that spark, it steps the voltage back down to a safe level.
Why is backing away from that spark so absolutely critical? One word: flashover. If your controller fails and doesn't step back that voltage in time, the spark turns into a full-blown electrical arc. This violent flashover will literally knock all the collected ash right off the plates and back into the high-velocity gas stream. We call that re-entrainment. And not only does it physically damage your expensive equipment, but it sends a massive spike of particulates right out the stack, instantly putting your facility out of compliance.
Section 6, the operator's loop. Finally, let's tie all of this complex chemistry and automation directly back to your daily responsibilities in the plant control room. Because at the end of the day, all this fancy hardware is only as good as the person running it.
The single most effective environmental control strategy often just comes down to the absolute basics: running a tight, highly efficient, and perfectly maintained plant. Finding and fixing boiler casing leaks prevents excess oxygen from fueling NOx creation. Maintaining your insulation prevents thermal losses that would force you to burn even more fuel. And running your equipment as close to its maximum rated load as possible ensures you're operating right in that peak efficiency window it was designed for. Remember, every single drop of lost efficiency translates directly into excess emissions.
So keep this core conflict top of mind the next time you sit down at the console. The grid is demanding more power, the outside temperatures are rising, but your environmental permits, they are an absolute hard line. Mastering that delicate, high-stakes balance between maximizing thermal output and keeping chemical control, that, right there, is the true art of power engineering. Thanks for hanging out with me on this explainer, and I will catch you in the next one.